All right, welcome everyone back to 264A Automated Reasoning. Today we'll continue with our discussion of applications. We will be mostly looking at probabilistic reasoning and the interplay between probabilistic reasoning and tractable circuits. We have actually two main segments of the discussion today. In the first part, we will look at how we can do probabilistic reasoning using tractable circuits. And the story that we will tell there will have weighted model counting as an integral part. In particular, we will see that to answer queries on models, probabilistic models like Bayesian networks, and in particular, marginal queries, we can actually reduce that to a problem of computing weighted model counts on a Boolean formula. And then we'll see that to do that, we can use tractable circuits. So in this first part, we're going to end up having a pipeline that starts with a Bayesian network and ends with a tractable circuit that does that computation in linear time with weighted model counting sitting in the middle. You'll see that that pipeline is actually not specific to Bayesian networks. In fact, it's not even specific to probabilistic reasoning. So the techniques that we will be looking at there are pretty broad, and they've been actually used extensively recently. They're everywhere now. So hopefully you'll be learning something very valuable and broadly applicable. Now, in the second part, we will look at that from a more abstract point of view. We're going to cut the middleman and start going directly from something like a Bayesian network or a model of that type directly into the tractable circuit at the end, and we'll study that relation in a somewhat more abstract way, and we'll motivate and tell you why that is actually important. But the short story is there's been a lot of development on this area, and people started using these techniques in ways that are different than was originally intended, which mandated this more abstract study of the relation between these computations and tractable circuit. It's a fascinating story. You're going to see there. And for those of you who may be familiar with some of these techniques, hopefully you will see some insights there that clarify a lot of connections, because as I said, there's been a lot of work on this area recently across many different dimensions. All right, let's go get started by heading to the whiteboard and go ahead and work on the first segment. So as this title on the slide says, what we're going to be doing first is looking at the reduction of probabilistic reasoning, in particular, the computation of marginal queries into weighted model counting. And as you know, we are working with Bayesian networks here. And as I said earlier, it doesn't have to be a Bayesian network, but that will make the discussion very concrete. Now, we know what a Bayesian network is by now. We have directed a cyclic graph like this one. People sometimes refer to this as the causal structure or causal graph. We have three variables, A, B, C. In this case, they happen to be binary. They don't have to be. In fact, what we will talk about will work for discrete variables. And we have these conditional probability tables, which provide these local distributions. So this is the distribution on A. This gives us the distributions on B for every state of A. And this last guy gives us the distributions on C for every state of A. Now, as we mentioned before, such a model specifies a joint probability distribution. And here's how it looks in this case. I have three variables, they're binary. I have 8 possible instantiations of these variables. And this Bayesian network assigns a probability for every one of these instantiations. And by now you know how to do that. Each one of these probabilities is just the product of 3 numbers. We pick a number from each one of these CPTs and multiply them. We've gone over this in detail last time. And the queries we're interested in are really with respect to this guy. And they're simple. Once you look at this table here, We talked about the most probable explanation, which effectively ends up being that I want to find a row that has the highest probability. And typically I give you an evidence or event, like the variable b has this particular value, in which case you want to restrict your search to those rows that are compatible with this evidence, right? That's pretty simple. And last time we saw how we can solve this problem by reduction to max set. So today we'll focus on the marginals query, where the goal is to sum the probabilities of instantiations that satisfy a given event. Meaning I give you something like the variable b has this value b2, and then you want to look for those rows that are compatible with this evidence and add up their probabilities. That's the query that we'll be focusing on today. Now, of course, both of these are trivial if you have this tabular format, but you don't have this tabular format. You have these guys that generate that. This is exponential, and these are usually not exponential. They're just local distributions. So I want to answer these questions by operating on this without having to generate this explicitly. That's basically the game. Now, to motivate the second part and to help you perhaps appreciate what we're going to be talking about, let me make the following observation. These techniques that we will discuss do not necessarily depend on this table being a distribution. In this context, these numbers are between 0 and 1, and they have to add up all to 1. And we call that a distribution in this case. It doesn't have to. The techniques that we will be mentioning will work for a broader class of applications when we have what we call a factor. A factor is just a table like this, except these numbers are just non-negative, right? And there is no constraint on them adding up to anything. So it's just a table that maps variable instantiations to non-negative numbers. And that factor doesn't have to be coming from a Bayesian network. It will be coming from other kind of representations. But the general idea is it is specified using some kind of factored representation like this. We're going to get to this later. But again, the point here is I want you to realize that the principles we're going to be discussing are way more general than the current discussions will suggest. Okay, let's go on. What we'll be doing is effectively showing you a whole pipeline where you go from a Bayesian network, and the goal is to try to produce a creature that allow you to do inference on that Bayesian network in time linear in the size of that creature. So we're going to go ahead and take that Bayesian network and write a weighted Boolean formula where the goal is if we do weighted model counting on this guy, then we solve that query on that Bayesian network. And then the way we're going to do this is by compiling into some type of a tractable circuit from which we're going to extract something that we're going to call an arithmetic circuit. And the point, once you have this guy, inference on this becomes a matter of just doing linear propagation on that guy. Now, we did sketch this at some level before. Now we're going to do it in detail, and we will do actually something pretty interesting, which is when you do this reduction, what information do you capture about that guy? So this guy has properties, and these properties fall into two types, what we call a global structure, which is the topology of the Bayesian network, and local structure, which are these numbers and their properties. And what we'll do today is we'll do a reduction first that only captures the topology of the Bayesian network, but is insensitive to what these numbers will work out regardless of what these numbers are. And then we'll show a reduction that is actually sensitive to what these numbers are. So it will actually pay attention to these specific numbers and take advantage of them. We will say that we're exploiting local structure in that case, and that is very significant for efficiently doing this, all right? So we're gonna see two stages going on here. And as I said in the second segment, we're just gonna cut out all of this middleman and study these relations directly, and that you will see is a very interesting story. All right, so we will start by reviewing weighted model counting. We talked about that before, but let's just now do it a bit more formally. We had some cartoons for that before. And this definition 11.3, some of these are actually coming from my book that is titled Modeling and Reasoning with Bayesian Networks. So what we have here is a propositional formula that is this guy over Boolean variables. Here are the variables. And then we have a set of weights. So there is this weight function that basically assign a weight for every literal. Now, this is a Boolean variable x. And in this notation, we're going to use small x to represent one particular value of this variable. So this guy, in this case, could be one of two, true or false. And these are what we called literals before. So what the weight function is doing is giving a weight for every literal. And now we define the weighted model count of this formula simply like this. This is the notation for it. What I'm doing is I'm iterating over every variable instantiation that satisfies that formula. This is what we called a world previously, right? So this is a world. And we're iterating over all of these worlds that satisfy the formula and adding up their weights. And the weight of a world is just simply a product of the weights of the literals that appear in it, okay? Straightforward. Okay, so think of it as every world has a weight. Every world has a weight, which is simply a product of the weights of the literals appearing in it. And when I'm computing the weighted model count of that formula, I'm just adding up the weights of its models. All right, and this is what we're going to call WMC, weighted model counting, and we're going to treat this as a function that takes a Boolean formula and come back with a number. Now, the reduction. And this is the very first reduction. The vanilla flavored reduction, the one I'm going to show you now, is the one that started this whole area. It's pretty simple, given what we know from last lecture. It should be somewhat familiar, at least conceptually. And we're going to illustrate it on this particular Bayesian network. So the idea is we're going to write a formula, a Boolean formula with weights. And the main thing is, what are the variables of that Boolean formula? So what we will have is two types of variables. The first is what we're going to call indicator variables. These are Boolean variables. And by the way, these are similar to what we used last time when we reduced MPE to max_sat. So basically, for every variable in the Bayesian network, like A, and every possible value, we're going to have one of these indicator variables. So A has two values that it got two indicator variables. Now, if A had three values, A1, A2, and A3, then you're going to get three guys here. And in this case, B also has two values, so it gets two indicators, and C also gets two indicators. This part is pretty simple. You're going to have an indicator variable for every Bayesian network variable and one of its values. Now, the second type of variables are called parameter variables. These are also Boolean, and these two types will be the only thing we're going to use. And this is now different from what we had in the previous reduction of MPE to max_sat. And these variables, which are also Boolean, are also simple. What we do here for every parameter in the Bayesian network, we have one of these guys. So this parameter, remember, this represents the probability that variable A takes the value A1. So I'm going to have a P for that and a P for the other guy. Now, if you look at this guy here, this is the parameter theta B1 given A1. So I'm going to have one of these guys. So last time when we talked about notation, we had this notion of theta. We notated these as theta C1 given A1. So basically, each one of these thetas gets one of these P's, an image of it. The difference is this guy is a real number, but this is a Boolean variable, okay? And that's it. And now we will see what the formula is. Now that we have our variables, we can talk about the Boolean formula, which is going to be in terms of these two types of variables. And what you'll see is the Boolean formula has two parts. One part we've seen before when we talk about the reduction of MPE to weighted max_sat, and the other part is new and specific to this particular problem. So here's our example. Here's our Bayesian network with its three CPTs. And the first type of clauses, which we will call indicator clauses, are just trying to capture the fact that every one of these Boolean variables must take a unique value. So here's how they look. I have variable A, and this clause is saying it must take the value A1 or A2, but this does not preclude the possibility of this variable taking both values. So we end up having this guy saying, yeah, but either this is not a value or that's not a value. When you put these two things together, that ensures that this variable will take precisely one value, either A1 or A2, and similarly for the other guys. Now, if the variable had more values beyond 2, as we've seen last time, we'll get more clauses. So in general, if we have a variable x and it has k values, x1 through xk, you're going to have this guy which says x must take one of these, and then you end up having a bunch of these guys that basically preclude the possibility of x taking more than one value. So you're going to have a quadratic number of clauses in this case, and together they ensure that x takes precisely one of these values, one and only one. Now, the other type of clauses are what we will call the parameter clauses, and you'll also see that they're pretty intuitive. Basically, for every one of these parameters, we're going to write a Boolean sentence, and here's how it looks. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I end up having 10 of these sentences. And you can think of them, they're grouped into 3 groups. Each group is generated by one of the CPTs. What's happening here? This is saying this indicator, if and only if that. You want to think of this as if the variable A takes that one value, then I must have this parameter. This is generated by the second entry here. Okay, this is a boundary case, not as interesting. Let's look at, for example, this row here, right? So A has the value A2 and B has the value B2. So this generates this particular guy here. Now, what does that says? You can think of it as the variable A taking this value and the variable B taking that value if and only if I have this particular parameter. And when we see why this reduction works, it will become more apparent. But the point here is, you can see how systematic this is, right? You just walk through the Bayesian network, and for every entry in a CPT, you generate one of these guys. And the general form of it looks like this. Think of this as coming from a parameter theta for a variable x, given that it has these as its parents. And this is a particular value of that variable x, and this is a particular value of its parents. Then I end up having the corresponding Boolean variable if and only if, and you can see what's going on here. These are the indicators for the parents, and this is the indicator for the guys. Pretty straightforward. That is the vanilla flavored reduction. We sketched this before, but now you can see how it works more generally for discrete variables. Now, we're still missing one thing to finish this reduction. Can someone suggest, what is it? I'm not done with this reduction, right? We need to say one more thing about it. The goal was to take a Bayesian network and write a Boolean formula so that if I do weighted model counting on the Boolean formula, I can answer questions or I can answer marginal queries on the Bayesian network. Are we ready for this? This whole thing is our Boolean formula. And someone is saying, where are the weights? Excellent, we need the weights. And the weights end up being straightforward. Remember, we have 2 kinds of literals here. And the weights have to assign a number for every literal. Now, we have the indicator variables, and they could be appearing as positive literals or negative literals. And then I have the parameter variables, the Boolean variables, and they can appear either positively or negatively. The weight simply says literals of indicators always gets the value 1. And negative literals for the parameter variables also get 1. So effectively, these guys are out of the picture in a sense. And this is the interesting part. The positive literals over parameter variables, they get the corresponding number. So help me out here. If I go ahead and pick this guy, what is the weight of this guy? Give me a number here. Give me a number for this particular parameter variable. This is a Boolean variable B2 given A1, and I want a weight for it. And let's see, someone is saying 0.9. Let's see, where is that guy? That is for variable B, B2 given A1, B2 given A1, it's this number here. Very good. Yes, yes. So that is the parameter. And if we're going to look at this guy here, what is the weight for that? That is also another 0.9. That's not fun. Okay. So that's it. You can take your Bayesian network, write out this Boolean formula, assign the weights, and here's the guarantee that you are going to get from this guy. The guarantee is, if n is your Bayesian network, and it does specify this probability distribution, and the guy is the CNF encoding. Now, what we wrote is not exactly a CNF, but if we break these bidirectionals into, two sentences, one in each direction, you get a CNF, but let's call it a CNF. So you've got a Bayesian network. It specifies this distribution, and this is the encoding we just saw on the previous slide. Now, if you give me any evidence, now, what is that evidence? These are variables and specific values of those variables. I'm trying to compute the probability of this guy, okay? All you have to do is take the indicators that correspond to these values, conjoin them with your formula, that is this guy, and compute the weighted model count. Guarantee that is the probability of that particular piece of evidence. And on the next slide, we'll see why this actually works. But the point is, I started with a Bayesian network. I ended up with a Boolean formula plus some weights. And now if I know how to do weighted model counting, then I'm basically done. Okay, so the story gets interesting just a little bit. Why does this work? Well, if you look at this Bayesian network and you look at the Boolean formula that we wrote, which is what we're calling the encoding, and you look at the models for this guy, right? The truth assignments. Now, this guy has a lot of variables, correct? I had 6 indicator variables for this guy. And I had 10 parameter variables, 6 indicator variables, because every variable in the Bayesian network generated 2 indicator variables. And I have 10 parameter variables because I have 10 parameters in the Bayesian network. So that's quite a bit. I'm going to show you now the models of this Boolean formula, right? And what you'll see is those models of this Boolean formula, the truth assignment over these 16 variables that satisfy this Boolean formula, they happen to correspond to the instantiations of this Bayesian network. Now, 16 variables, that's a lot. So there is 2 to the 16 possible truth assignment. But believe it or not, this guy ended up having only 8 models. And this is a busy table. Let me explain it. Focus on the middle part. The middle part are the truth assignment that satisfy this Boolean formula. Now, because we have so many variables, I'm only writing those variables that gets the value true. So 1, 2, 3, 4, 5, 6, those guys are getting the value true. Missing here is a whole bunch of other variables, a whole bunch of indicators and a whole bunch of parameter variables, but all of these guys get the value false. So I'm only showing you those guys that get the value true. And this encoding has precisely these 8 models, which correspond precisely to the 8 possible instantiation of this guy. Now look at this guy, A, B, C, each 2 values. Here are the different combinations. Let's look at the first one. Here's this guy. What's happening here? This indicator is true, which corresponds to this value. The other 2 indicators, A2, A3, sorry, there's no A3. the other indicator, which is IA2, that's false. And this guy corresponds to this guy corresponds to that. And out of the 10 parameter variables, only 3 gets the value true and the other guys get the value false. And look, which ones did end up getting the value true? Those are the parameters that we have to multiply their values to get the probability of that guy. Right? Those are the parameter variables that are compatible with this particular variable instantiation. Now, if we go and try to compute the weight of this variable instantiation, we only have to worry about these guys. The negative ones, by our weight function, they all get the weight of 1, so we can ignore them. Now, this also has a value of 1. This has a value of 1. This has a weight of 1. So the only guys that contribute to the weight of this truth assignment are these 3 guys, and we know what these guys are. The weights of these are precisely the corresponding parameters. So if I compute the weight of this variable instantiation, I get this number, which is precisely the probability of that Bayesian network instantiation. So this reduction, or this Boolean formula, was crafted so that it has precisely these kind of models that are in one-to-one correspondence with the variable instantiations in my Bayesian network. And the weight function was crafted in such a way where the weight of this guy is precisely the probability of that particular guy. So now if you go and tell me, okay, I'm interested in this probability, the probability that this variable A will take that value and that the variable C will take this value, according to our theorem, you build these indicators, the indicator for this, the indicator for that. You conjoin them with this formula and then compute the weighted model count. Now, what does it mean to take this and conjoin it with that formula? That means you look at the models, you're throwing everything out except the ones in which A1 and C2 hold. And that end up being this guy and that guy here. So you're basically adding up the corresponding weights and you're getting this number, which is precisely the probability that you want, okay? That's what's going on here. Now, it gets interesting in just a second because I want to do a little bit more than this. And that is to capture more properties of the Bayesian network when I do the encoding. So, and this gets us into this notion of a local structure. This is pretty important. And even though this concept is pretty old, it's resurfacing now, and people are actually using this in a variety of other contexts when going beyond Bayesian networks. So I'll explain this in just a second. What is local structure? Local structure is when we start paying attention to the numbers. And people have identified 2 kinds of local structure. Again, this is in contrast to global structure, which is the topology of the Bayesian network. One of the things is what we call 0-1 parameters, like we have here. So by the way, what happened here is I took the previous example and I changed the numbers. We're working with the same example as far as the topology of the Bayesian network, but we're working with different set of parameters. So what does this mean? This effectively means that when A is true, B cannot be false because the probability of B false given that A is true is 0. That's like a logical constraint. And in this case, if you look at the distribution over B, when A is true, what do you get? You get a 1, 0. What does that mean? That's basically saying that when A is true, I know for sure that B is true. Similarly here, this is saying when A is false, I know for sure that B is false. So actually you can think of this table as specifying a logical equivalence between A and B. It's like, that's what's going on. Now, I want you to make a distinction here. It's not apparent in this particular case, but when you have the situation like we have here, that once you tell me the value of A, I know for sure the value of B, we will say that this table specifies a functional relation or a functional dependency because B is just a function of A. There is no probabilistic reasoning. We're going to use that term later. That became significant recently. So in this case, when you have zeros, and ones in this particular case, they implied a functional dependency between B and A. Now, zeros do not necessarily imply a functional dependency. For example, B may have 3 values and 0 may be attached to one of them, but not the other 2. Then that means if I know the value of A, I rule out one of the values of B, but then I'm not sure of which one of the other 2 it is. So in that case, the 0 is a logical constraint, but does not elevate to the level of a functional dependency. A functional dependency is when the zeros eliminate every possibility but one. Okay, a fine distinction will become apparent in the second segment. Now, that is an example of a local structure. The other example is what we call equal parameters. And in this case, what happened is in some of these tables, numbers are equal. These are equal. These are equal. These are equal. Now, the second reduction we're gonna show will be able to exploit those kind of relationships and will produce a more efficient reduction. Now, I hope at least you can see why taking advantage of 0 parameters may help, because 0 parameters eliminate possibilities, and you'll see the reduction, second one, will be relatively simple, and it will use the fact that the values of some parameters are 0 to eliminate possibilities. Okay, that's obvious. Now, what is perhaps not obvious is why does the fact that 2 numbers being equal helps? Well, it's not illustrated in this example, but let me show you another example. Equal parameters typically imply a very interesting type of information that is known as context-specific independence, or CSI. Let me show it to you. That's a big deal. Think of this Bayesian network fragment. I have X and Y, and I have a child Z. And let's look at the CPT for Z, and suppose it looks like this. What happened here? I'm not showing the whole thing. I'm just showing you half of it. This says, here's the 2 distribution. This is one distribution over Z, given that X is true and Y is true, right? True, 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 and here's true, false. And this is another distribution on Z when X is true and Y is false. And there's 2 more distributions, but look what happened here. These are the same. What this says is, hey, when X is true, the value of Y doesn't matter anymore. Right? When X is true, this is my belief in Z, and it happens to be the same if Y was false. So what does that mean? That means when this guy takes the value true, this is no longer relevant to that. So as if this edge is conditional, and it will disappear when X gets the value true. Now, this may not be the case when X is false, and that's why it's called context-specific independence. Someone said this should be false here. Thank you. So what happened here is I have an independence between Z and Y. Z is independent of Y, but only when X takes that particular value T. This information is very valuable computationally. And it's not a kind of information that you can infer by looking at the topology of the Bayesian network. You have to look into the parameters. And this is what we call context-specific independence. Context-specific independence because the context here is that X has the value true, all right? And this is to be contrasted with structural independence, independence that you can infer by looking at the topology of the Bayesian network. So this new encoding that we're going to show can actually capture context-specific independence, and that can have a dramatic impact on how easy it is to do weighted model counting on the resulting formula. To further our intuition about what's going to happen next, let me just point something. Guys, this is really important. And from a practical point of view, this is the example we started with. And this is the example now we're working with. They're the same Bayesian network structure. The only difference between them is the values of the parameters, right? The encoding we just looked at will generate the same formula for either of these guys. So this guy which just worked will be produced by this or by that, because this guy does not look at the values of the numbers. It's not sensitive to what these numbers are. And you can see that this is a missed opportunity, because we know, at least intuitively, the fact that I have zeros and ones, the fact that I have numbers, parameters that are equal, this should be easier to do inference with than that. Okay, you have to just believe me on that part. And this is not taking advantage of that. So now we're going to see an example of a reduction that takes advantage of these numbers. And maybe you can even help me with it because it's actually pretty intuitive. And that would be just an example. So here's how we're going to handle zero parameters. Let's start with that. We're going to look at first zero parameters. If you look at this situation here, this is an example of a zero parameter. And this guy corresponds to that guy, right? Now, in this encoding that I generated, I have this guy. Now, what is this trying to do really? If you understand, if you look at the semantics of how we explain this encoding, what is the role of a sentence like this? The role of a sentence like this is for those models in which the variable A takes this value and the variable B takes that value, I want to make sure that I multiply the value of this parameter when I'm computing the weight of that model. Okay, we here switch from the notation A1, A2 to A and A prime. That's okay. Right. What is this guy trying to do? This guy is trying to make sure that the value of this is multiplied by the weight of a world in which A has this value and B has that value. But I know that this guy is zero. What does that mean? I'm just going to be multiplying a zero and the weight of any world in which A is true and B is false is now guaranteed to be zero, correct? So that world is not going to play a role when I'm doing weighted model counting, correct? So what do? I can get rid of this guy altogether and replace this by that, which says you can't have that combination. And I threw out one of the worlds. And the world that I threw out, I know for sure has a weight of zero or probability zero. So I actually got rid of having to represent this variable explicitly, and I simply produced a Boolean formula that has basically fewer worlds. And every world that I eliminated, I know for sure has the probability or a weight of zero. Okay, so that's pretty simple. So we basically get rid of this guy and replace it by that. Now, the same thing, same observation for a one parameter. So this is this guy, parameter one. What is this trying to do? This is part of this guy. It's trying to make sure that a world in which A is true and B is true, that weight of that world get multiplied by this guy. But this guy is one. So that doesn't do anything. So I can just drop this guy and I haven't changed anything. If I take the Boolean formula and generate the worlds and compute their weights, that's not going to change anything. And then the last kind of thing is when we have equal parameters. So in this case, C given A, this guy and that guy, they're equal. This statement is making sure that when A is true and C is false, multiply by the weight of this guy. When A is false and C is false, multiply by that. These two numbers are the same. I can merge them into one variable and do this. And this guy now will have the same value that these guys had. Okay, so you can see now that once you know the weights of the variables to be either equal, 0, or 1, you can modify your encoding and generate a Boolean formula that has different properties, but still without changing the definition of your weighted model count. So if we look in this case, what will P1 be in this case? P1 will get rid of these guys and we'll have this instead, and this guy will have the weight of 0.8, right? So it's just a surrogate for these two guys, right? So let's look at it. This is the encoding without local structure. And this is the encoding with local structure. These guys did not change. The indicator clauses did not change, but these guys changed. And now they're simplified to this, right? So if you look at these guys, these were the 0, 1. Two of them were dropped and the others were replaced by these guys. So this guy here became that. And these two were merged by this, and these guys were merged, producing that. And now we have three variables, new variables, 1, 2, and 3. We basically got rid of everything here, and we have 1, 2, and 3, and these are their corresponding weights. So this is the guy that we actually have. And that will produce the same table, right? Now, we're going to try to finish this story off by saying, good, you got a flavor now of what's going on here and how you can actually capture local structure. So what do I do next? Well, you can go and just run a weighted model counter on this, but we're actually going to go ahead and take this all of the way and use our tractable circuits. And that's going to be significant for the rest of the story as well. So what am I going to do? I'm going to take this guy and I want to do weighted model counting on it. Now, from the circuit types we looked at, the ones that allowed us to do model counting and weighted model counting were those that were decomposable, deterministic, and smooth. So I'm going to take this guy and compile it into an NNF circuit that's decomposable, deterministic, and smooth. And that's what I'm going to get in this particular case. Okay, I'm going to just show you one more transformation on this that gets you ready to do weighted model counting on this guy. And we've sketched this at some point, right? So what we're gonna do is, instead of saying, okay, set these guys in a certain way, multiply, add, we're just gonna go and generate that guy that does that computation. So we're gonna replace ands by multiplications. We're gonna replace or by additions. Negative literals, remember their weights were 1, we're going to replace them by 1. Positive literals, we're going to replace them by their weights. The only guys that we're not going to replace by their weights are the positive indicators. And why? Because I'm not just only interested in counting the models or the weighted models of this, but I want to do it under different pieces of evidence. So I'm going to keep those guys so I can change them later to capture evidence. But otherwise, aside from these guys, I will replace the literals by their weights and replace the ands by multipliers, and I'm going to replace the ors by adders. And that's what I'm going to get back. Now, I did everything that I mentioned, but I also changed the notation. Instead of using this guy, I'm using this, which is more of the standard. This is the same as the indicator variable, okay? And that's what we're going to go in an arithmetic circuit as opposed to a Boolean circuit. We have the indicator variables, we have constants, multiplications, and additions. That's your guy. Now, you're ready. This is doing weighted model counting, right? When you look at that guy, but I'm just doing it directly. And let's see it. It's fun, okay? So here I am. I got this guy, and let's go ahead and use it, right? So help me out here. If I come and tell you I have no evidence, and what is the probability of that? So I'm doing, in this case, weighted model count on the original Boolean formula with no evidence. You guys know what to do when you have evidence and dealing with indicator variables. You replace these guys by zeros or ones depending on whether they're compatible with the evidence. So in this case, no evidence, that means forget about this, we'll look at it next. Everything here will get a 1. Let me ask you a question. If I propagate, what number should I get at the top in this case? You should be able to predict this. This circuit will be adding up the weights of every row. And someone is saying I should get a 1. Absolutely, because the table of a Bayesian network is normalized. That's up to 1. So actually, if you do the computation, you're going to get a 1 there. Now, let's look at this guy. I want to compute the probability of this. B has this value, C has that value. And in that particular case, what is going to happen to these guys? Help me out. Here, 0 or 1, 0 or 1. This guy, remember, if it's compatible with the evidence, it gets a 1, otherwise it gets a 0. 0 or 1 here, 0, 1. How about this guy? This guy, 0 or 1. This guy, it is compatible with this, should get a 1. And this guy compatible should get a 1. So that's what I'm going to get, okay? This got a 0 because it's not compatible with this. This got 1, it's compatible. And if you go ahead and propagate, you're going to get a 0.1 at the top. That is the probability of this piece of evidence. Beautiful. You see what happened here? What happened is I started with a Bayesian network. I wrote a Boolean formula I converted that Boolean formula into attractable circuits that's decomposable, deterministic, and smooth, and I extracted this guy from it. And I'm now ready to do linear time inference that is linear in the size of this particular circuit that we're calling an AC. And just to show you what might happen if you encode versus not encode local structure, when we dealt with this guy, we had two encodings. If you were to take the first encoding and go through the pipeline, you're going to get this circuit. This is what we got from the second encoding. Both will work, but look what happened here. Look what happened. Here, I'm not putting the actual values. I'm keeping these guys because this circuit will work regardless of what the values of these guys are. So I compiled a circuit for you that is independent of the fact that this is a 0.5, this is a 0.5. So if you were to go and change your numbers here, this will still work. Just make sure you plug in the right values there. This, no. This is specific to the fact that these were the values. You expect this to be more efficient, okay, than this guy. And sometimes the difference could be exponential, right? You may not be able to do this guy, but when you use the values of the parameters, you will get something that is actually efficient and compact, right? So you see the importance of exploiting local structure. Okay, let me just have a couple of additional remarks before we leave this subject and end our first segment. Now we're going to get back to these guys. The whole second segment will be about these arithmetic circuits because the story gets really interesting there. But let me make a couple of remarks here. One of them is, if you look at the computation of marginal probabilities on Bayesian networks, right? So before this technique was introduced, there's decades of research on that. So if you look at the standard textbooks on Bayesian networks, including my book on this, you're going to find chapters dedicated to algorithms that are not based on this. And these algorithms, there are things like something called variable elimination, join tree, They are known to have this complexity. So they're linear in the number of variables in the Bayesian network and exponential only in this parameter called tree width. And tree width is a number, graph theoretic number that captures how connected the Bayesian network is. So as you go this way, you expect tree width to start going up. This is a heavily studied notion in graph theory. And the method that I gave you, the first encoding, the vanilla flavored encoding, comes with this guarantee as well. So if you do the compilation in a certain way, you're guaranteed to be within this complexity. So you cannot do worse. But if you exploit local structure, you can be significantly better than this. And this is one of the competitions that took place at the conference known as UAI, Uncertainty in Artificial Intelligence, which is basically focuses on probabilistic reasoning and similar methods, particularly graphical models like Bayesian networks. And there was some suite of Bayesian networks that were actually generated from higher level representations. So they have a lot of local structure, massive logical constraints, context-specific independence. And here you see the systems that were based on classical algorithms that do not take advantage of the parameters. They just look at the structure. And this is a system that is based on what I mentioned to you. And you can see that it actually solved all problems in this case. These guys, does it even say here? I think these guys had the large tree widths. So if you have an algorithm that is exponential in tree width, this is not surprising. And this method that I've mentioned was able to solve these problems even though they had a very large tree width because they were actually encoding local structure. So techniques becoming basically used everywhere. One of the popular areas these days in probabilistic logic programming where they do these kind of reductions. Let me just conclude with a couple of more remarks. I just gave you 2 sample reductions. The vanilla flavored, and actually I introduced that in 2002. and one of the ones that take advantage of local structure. And it's not the best one available. There is more, but they're a little bit more intricate to explain. There are other reductions proposed by people which try to deal with this situation when a variable has too many values, because the reduction that I showed you end up being generating a quadratic number of clauses. So there are better ways to handle that. Sometimes you can play all kind of tricks because of your knowledge of logic and reduce the number of clauses in the CNF that is generated without affecting its ability to do the right computation and so on. And finally, I want to mention one more thing. I was hoping to spend more time on it, but let me just put the hook for it, and maybe next time we will we'll talk about it. Two observations, because and we're going to put pointers for these papers if people are interested. So when you get your AC, you can not just evaluate it, you can do a backward pass on it, which is back propagation in neural networks, and compute the derivatives of the output with respect to these indicator and parameters. And those end up having specific meanings. They give you more marginals. So really, if you have this creature, you are in heaven in a certain way. You can do one pass upward and another pass backward, and all of these derivatives are meaningful, and they give you all kind of probabilistic computations. So this is a very rich creature. We don't have time to go over all of these details. And I think I'm gonna leave it at that because we're already way beyond our break time. So let's take our break time now, and let's get back at 11:05. I know I'm eating up 2 minutes from you, but that's fine. So 11:05, we will resume our discussion.